Okay, so remember from before I talked about turbulent flows, you have this, right, the look of the flow, which is important because we look at things as fluid dynamics, right, is you have a sort of mean velocity, u bar, and then you have these variations, right? So actually the velocity is a function of this mean that you only can get from an experiment actually, so that's the inherent empirical part about turbulence, plus variations. We actually need that too. But theoretical models exist for relations about these and these. Right. Again, we're trying to get these friction factors, so let's just be inspired by what we did in the laminar case because it worked out and was so nice, right? So when it was laminar, right, we figured out, right, that u of r was, right, right, from the shear assumption, right? Once we had this UR, then we got flow rates, we got flow rates, we got these V primes, and we got V maxes, right? All from figuring out what this velocity function was. And that was analytical, and that's for the laminar case. That's specific to laminars, the fact that we could go from physical equations, derive what the u of r was, and then get our quantities. It comes from assumption, but it's okay. So right, if you look at the same velocity profiles for turbulent pipe flows, they kind of look like plug flows, right? This is a quadratic profile. This is sort of steep. This is steep at the walls, right? And you can measure these things and people just realize if it was turbulent, you get profiles that just look steep, right, pretty steep at the wall. So just the only difference that's going to really happen in terms of these analysis, or the analysis of things that we're doing, is instead of getting to this u of r analytically from a force balance, it comes from empirical natures of experiments that then are verified through scale arguments. But either way, I'm just going to give you this. Get this log wall relationship. So people came about and realized that this works pretty well. Here's the experimental values. Those are experimental values, right? So the kappa is always 0.41 and the b is equal to 5. So right off the bat, you kind of know where the story is going to go, right? What's going to happen is we're going to take this thing and do the exact same processes to get friction factors. That's it. Once we have that, story's done for friction factors. So I want to show you, though, that you can do this in the next video. So actually, I'll put that up one more time. Right, this is the velocity profile that people realized. Right, and this is for, if you're looking at here, not in radial. That's what they're from. So that's the plan there. And then I haven't really told you what this plus sign stuff means yet, so I'll define that here right now. This is, again, non-dimensional, where the plus is what it's doing is it's taking the dimensional velocity and dividing it by something called a friction velocity. Friction velocity equal to this. And then y plus is equal to Y star. Or this is the, right? Right? Remember, that's what that. So those are all the ingredients that are going to go into getting the question of what is the friction factor when the velocity is turbulent.